Okay, so we've done eigenvalues of 3 by 3, but what about eigenvectors? It can be a little bit more tricky. Well, one thing you might notice about this matrix is that it is actually singular. And you can see that, for example, by saying that bottom row is just minus the top row. The matrix is singular. It's really only got two equations. It's singular, so it means one of the eigenvalues is 0. It turns out that the eigenpairs, if we like, are 0 is the eigenvalue for this vector, and the other eigenvalues are minus 4 and 3. And we'll see how to work that out in a moment. But let's just check that they work, because when you've worked out eigenvalues and eigenvectors, you really should slap them in and check that they work. So working backwards in a way. So for example, if we call this vector v3, lambda 3 is 0, then 1, 6 minus 13 times this vector, if you just check it, 1 plus 12 minus 13 is 0, 1 times 6 minus 6 is 0, and of course this one is just minus. So comes to 0, which is 0 times the original vector. So the eigenvalue is 0. Of course, we could have taken any multiple of this. And if you see what this is doing, this is actually a relationship between the columns. In other words, 1 times the first column plus 6 times the second column equals 13 times the third column, which is slightly harder to spot than the relationship between the rows, which is just that row 1 is equal to minus row 2. But of course, there must be a relationship between the columns. Okay, so we get that. We can get that solving by Gaussian elimination, and then yeah. So so we could use Gaussian elimination to solve that. Okay, so we'll come back to this in the review session and do some more examples of this. But in each case, all you do is solve the system, and typically you'll get one eigenvector. So you get one unknown parameter when you do Gaussian elimination to solve it. Okay, so I wanted to show you a use of matrices, and diagonalizing matrices is one of the use of eigenvalues and eigenvectors. So what does it mean to diagonalize? Well, if you've got a matrix A, then you can write it sometimes as a diagonal matrix with another matrix P and P inverse on the other side. So it's sort of this matrix D, this diagonal matrix, kind of equivalent to A. And if you think of P as maybe some kind of rotation, that doing A is something like rotating P one way, multiplying by the diagonal, which scales it in each of the axes, and then rotating back. So it's a useful way of understanding what the matrix does in a geometric way. But mainly the point is that diagonal matrices are much easier to deal with. Everything with diagonal matrices is easy. So if we can sort of convert a matrix into a diagonal matrix that's related to it, this is a handy thing. So this operation of doing P something, P inverse, is called a similarity transformation. And so if matrices are related by doing P on one side and P on the other side, we say those matrices are similar. It's a similarity transform. So if you just a similar matrix doesn't mean they kind of look a little bit like each other. It's a technical definition of similar. Okay, so how can we find a diagonal matrix that is similar to our original matrix? So it turns out that eigenvectors are just the thing we need. The thing is, AX equals lambda x for each of the eigenvalues lambda k and eigenvectors xk. It's the same as if we put all the eigenvectors in columns in a matrix. So suppose we've got n different eigenvectors, so we're lucky in this sense. And then we just arrange them in a column. And then you do A times this vector. It's the same as doing A times x1, A times x2, A times x3, because that's the way matrix multiplication works. It works by the matrix on the left multiplying the columns in the matrix on the right. So of course AX is lambda x for each of their lambda k and x k's. So we get the same matrix back but with the rows multiplied by lambda. And then you just have to check that if you multiply on the right by a diagonal matrix like this, if you see what it does, and it's kind of easier to sort of take the columns on the right and have them dive down onto the rows on the left here, that if you multiply by a diagonal matrix on the right, then it multiplies all the columns by the numbers on diagonal. It turns out if you did it the other way, and you can check this, an example if you like, that if you multiply by a diagonal matrix on the left, it multiplies the row by a constant. And it's this thing that we thought about a little bit when we were doing row operations. So what we've got here is that we make a matrix of eigenvectors, of different eigenvectors for hopefully different eigenvalues here. So we've got a complete set of different eigenvalues. Then A times this matrix of x's is x times the diagonal matrix. And if you just look at our original thing that we're after, you could pop p up onto the other side. In other words, multiply on the right by p to cancel it. This is the same as saying AP equals PD, where D is the diagonal matrix. And that's the form that we've got. If we call this matrix P, we've managed to diagonalize it. So we call P the matrix of eigenvectors, assuming that we've got n independent different eigenvectors. And D is a diagonal matrix of eigenvalues, which some people write this like diag, and then list. It's just a matrix with those on diagonals. So AP equals PD, which is nearly what we want. If P is non-singular, which means, of course, that the eigenvectors are independent, and certainly if the eigenvalues are all different, we've got n different ones, and the eigenvectors are independent, so the matrix P is non-singular. In that case, we have diagonalized it. In other words, we've shown that the matrix A is similar, in this special sense, to the diagonal matrix of the eigenvalues, and the matrix that does that diagonalization is the matrix of eigenvectors.